Dear colleagues, hello and welcome to the day 4 of the BRICS Young Scientists Forum in Materials Science session. Today we have another group of presenters and we'll start from Brazil. But I also want to announce you that later you will receive the contacts of all the BRICS representatives from each country. So please pay attention that you can contact them. All right, let's proceed to the reports, and the first presenter is Felipe Bonne from Brazil. Hello, Dr. Bonne, can you hear me? Yeah, start your presentation, please.
Okay. Hello, everybody. I hope to. That's right. Okay. Hello, everybody. I hope to
Hello.
find you in health and well. First of all, I'd like to thank for the opportunity to talk a little bit about our investigations on magnetization dynamics in magnetic systems. So, our studies on dynamics started in Santa Maria, in the south of Brazil, then proceeded in Rio de Janeiro, and now are being performed at the Universidade Federal do Rio Grande do Norte in Natal. I invited you to visit our university, which is a very nice federal institution with the bonus of breathtaking natural beauties of the city of Natal. So, magnetization dynamics is one important field challenge in the scientific community. It is of paramount importance in the context of fundamental science to bring information on how magnetic systems work. Moreover, it is also a key field from technological point of view, given magnetic materials are used in a broad range of applications. Specifically, the main question here is, how does magnetization behave in a magnetic field? I emphasize we find different kinds of magnetization dynamics according to the stimulus field and the probed characteristic time scale. For this reason, it's fundamental to employ different techniques to investigate the dynamics. Here I'm going to address two effects, magnetic effects studied by our group, which cover from domain wall motion up to magnetization precession. The first is the Barkhausen effect, which is focus of my study since I was an undergraduate student. Barkhausen corresponds to the voltage pulses induced in a sensing coil wound around a ferromagnetic material submitted to a smooth, slow-varying external magnetic field. The pulses are associated to sudden changes of magnetization due to the irregular motion of the domain walls. And the noise is composed by a series of Barkhausen avalanches with broad range of sizes and durations, which are focus of a wide statistical analysis. Since the discovery of the effect, Barkhausen have been employed as a non-destructive testing to investigate ferromagnetic materials. From this perspective of material science, for instance, we investigated this effect in non-oriented electrical steels. Then combining Barkhausen effect and magnetostriction experiments, it was possible to split magnetization curve and different regions according to the magnetization mechanisms, which are directly related to the energy losses in the material. This kind of study is very important because such materials are widely used as in equipments as engines and generators. However, Barkhausen effect has attracted increasing attention in the last decades due to its association to complex systems and the so-called crackling noise. Crackling noise arises in a diversity of systems, and all these systems have a critical behavior. The response of the system is to a field or a force is an irregular signal composed by avalanches with different sizes and durations. And despite the diversity in essence, they share statistical properties, and the exponent described in the statistical functions are dependent on general features of the dynamics. In this sense, the noise is a fingerprint of the system, but it can provide insights on all systems with crackling noise and on the physics behind such phenomena. Within this context, we performed a wide statistical analysis of the Barkhausen noise in ferromagnetic films, having variable thicknesses and different structural features. In this task, we consider the distributions of avalanche size, avalanche durations, the average size as a function of duration, and the power spectrum, each one described by an exponent. When considering polycrystalline films, they are divided into two groups according to the exponents, suggesting two types of behavior. By comparing experiment and theory, we interpret films above 100 nanometers exhibit a three-dimensional magnetic behavior with long-range interactions, while films below 100 nanometers are two-dimensional with long-range interactions. Thus, we revealed a dimensional crossover associated to the type of domain walls. For the case of amorphous materials, there are also two universality classes. In addition to the dimensional crossover, we found a change in the interaction governing the dynamics, passing from short to long-range interactions as the system goes from 3 to 2D. Thus, we identified the key to understanding the Barkhausen statistics in films resides in the interplay between system dimensionality and range of interactions. Going beyond, we also have obtained the average temporal avalanche shape, which provides numerous information on the inner structure of the avalanche. Notice the remarkable agreement between the experiment in the left and the theory in the side and the right. These results are very important because they were observed for the first time in films, as well as shown the average shape is a sharp tool to investigate crackling noise. On the second effect, and directly related to the material science, we look at the dynamics through the magnetic impedance effect. Magnetic impedance corresponds to the variation of the electrical impedance of a ferromagnetic conductor submitted to a magnetic field. It's notable that the impedance is dependent on the field, the frequency of the electric current, as well as it is influenced by features of the samples. So many studies can be carried out to obtain new materials with optimized response. ME technique is a promising tool to investigate nanostructures, the physics associated to the magnetization dynamics, as well as it has potential for application of magnetic materials in sensors. In the last decades, our group investigated different systems. Here I'm going to focus on the results obtained for planar systems, such as films and multilayers with different features, all with thicknesses of nanometers. Films and multilayers with uniaxial anisotropy often present symmetric curves with dependence with field and frequency. The idea here is to understand the shape of the curves and relate them to the mechanisms responsible for the impedance changes. However, it's important to notice that the curves do not show a linear response at low fields, which can make difficult the application of these materials in devices. However, when considered a system composed by a ferromagnetic layer coupled to an antiferromagnetic material, we're able to shift the curves in field, thus obtaining such linear behavior around zero field. These results become more impressive when comparing theory and experiment. In this case, notice the agreement between them. From this, we can describe the main features of the curves, as well as manipulate them by changing the field frequency and the sample. In order to obtain a linear response at low fields, we also studied the effect in tri-layers consisting of two ferromagnetic layers with different magnetic features separated by a non-magnetic material. In this case, by varying the thickness of the spacer, we verify an evolution of the magnetic impedance curves. We can also change the shape of the curves, keeping the thickness of the spacer constant, and varying the frequency of the experiment. In this case, we obtained asymmetric magnetic impedance curves. In a sense, you can turn the linear response of the magnetic impedance as low fields by changing the sample or experiment parameters. In another work, we manipulated the magnetic properties of materials by applying stress to magnetostrictive films grown onto flexible substrate. The changes in the magnetic properties are directly reflected on the impedance response. Observe the agreement between experiment and theory, which allow us to envision the use of such samples in flexible devices. Finally, more recently, we investigated the magnetic impedance in systems with magnetic insulators. We produced a system that consists of an yttrium iron garnet covered by a copper layer, and found that despite the different electrical features, the response is very similar to that obtained for magnetic conductors. These results are very important because yttrium iron garnet is a material with great appeal in the context of spintronics and to the development of devices with optimized energy efficiency. In summary, I gave you here a brief overview of two research lines developed in Natal. From Barkhausen noise, we may obtain information on the magnetization dynamics in nanostructures, as well as the insights on systems you cannot control in the lab, given the interdisciplinarity of the topic. From the magnetoimpedance effect, we probed the dynamics at high frequencies, and the results placed the investigated nanostructures as candidates for sensor elements for low field detection in devices. At last, I would like to thank for the opportunity, the institutions that support our work, my colleagues who worked hard to make it possible, and all of you for your attention. Thank you very much.
Dr. Bon, thank you very much for your interesting presentation. If there are any questions, please, dear colleagues, we have time to ask Dr. Bon. Thank you. Let's wait a bit if anyone is asking. Otherwise, I remind that you can forward the questions to the personal cabinet of Dr. Bon and find his contacts. All right, if no questions, let's proceed to another speaker. The next speaker is Dr. Yuri Illarionov from Russia. Dr. Illarionov, hello. Hello.
Can you hear me now?
Yes, I'm hearing you. So,
okay.
Hello, you can start your presentation now.
Okay, thank you. My name is Dr. Yuri Illarionov. I am researcher in EOF Institute in St. Petersburg, Russia, and currently I am on a long trip to Technical University of Vienna in Austria. And today I will show you some results on next generation nanoelectronics based on 2D semiconductors and fluoride insulators. So here's a brief outline of my talk. First I will say a few words why we need 2D materials and what kind of 2D materials we have from graphene to silicon. Then I will speak about why we need 2D materials for field effect transistors and emphasize on the general problem, which is the lack of scalable insulators for these new technologies. And then I will show you my main results on MOS2 transistors with 2 nanometers crystalline calcium fluoride insulators, and say a few words about further development of fluoride 2D nanoelectronics. So, as you all know, the era of new 2D nanoelectronics started from graphene, when Russian scientists Andrei Geim and Konstantin Novoselov got the Nobel Prize in Physics for the studies of field effect in graphene in 2010. But unfortunately, graphene has a zero band gap, and that's why it is suitable only for analog device applications and basically useless for digital field effect transistors. And that's why further research attention of scientists working on field effect transistors switched to such materials like transition metal dichalcogenized like MOS2 and other materials like shown here in this periodic table. So it's transition metals and such metals like chalcogens, like sulfur. And this TMD already have quite sizable band gap of 1 to 3 electron volts, and they are very attractive for digital devices because also they exhibit reasonable mobilities. And next 2D materials have been black phosphorus, and this material, in contrast to most TMDs, it can enable ambipolar device behavior, so both p-FETs and n-FETs as required for integrated circuits. The only problem was its poor air stability, but in our quite recent study, we addressed this and found that by encapsulation, conformal encapsulation, you can enable long-term stability ranging up to years for these black phosphorus devices. But now there are also more exotic materials like silicon, for example, which is 2D counterpart of silicon, but the problem is the same, quite poor air stability, but nevertheless, it was already demonstrated that working devices with silicon can be produced, as shown here. And even more exotic materials like germanium, stannene, and other counterparts of normal 3D materials, which can be realized in 2D. But why we actually need 2D materials for field defect transistors? As you know, the trends in modern electronics are currently driven by Moore's law, according to which the number of transistors on integrated circuits doubles every 1.5 years, as shown in this graph. But currently, there are some fundamental issues in Moore's law, so it's close to the end because of short channel limitations. For example, we have band-to-band tunneling in silicon transistors due to depletion regions for small channel geometries. And while previously we could enable cheaper and higher performance electronics, like shown here, in 1983, Dynatac mobile phone costed about $4,000 or 8.5 for current exchange rate, and now Apple iPhone just $500. And we want to continue this, and in order to do this, we need to scale down channel geometries even below 10 nanometers. And in silicon transistors, it's not possible because of the short channel limitations. And thin layer 2D materials, according to our understanding, they should help us to extend Moore's law and make electronics cheaper and more productive as it was happening during the last few decades. But the main problem of 2D electronics is that we not only need 2D materials for the channel, but we need insulators which should perfectly match 2D materials. In silicon technologies, you have silicon dioxide, which forms nice native interface with silicon. But when you place 3D amorphous oxide onto 2D materials like MOS2, you see that the interface is not very good because of dangling bonds, which reduce the mobility, and also oxide defects will perturb stable device operation. And possible alternative is hexagonal boron nitride, HBN, which forms nice interface, and also calcium fluoride, which we suggested recently, which also forms very nice interface. But another criteria is that you need to scale down the insulator thickness, and when you scale down some insulators like HBN, which have small dielectric constant and narrow band gap, you see that the tunnel leakage currents are very huge through such material like HBN. So here we show modeling results for equivalent oxide thickness of 0.5 nanometer and 1 nanometer. But for such material like calcium fluoride, the tunnel leakage is relatively small, which is quite satisfying for us. So this material basically satisfies two main criteria for insulator for 2D electronics: high interface quality and low leakage, and that's why it's so attractive, as we think, for next generation 2D electronics. And recently we took 2 nanometers thin calcium fluoride and transferred MOS2 of 1 or 2 monolayers on top of it, and demonstrated working devices, field effect transistors, which are world record thin, published this in Nature Electronics. And indeed, calcium fluoride could provide ultra-scale dielectric layers for the development of next generation 2D electronics. We performed analysis of the devices, did CM and TM measurements, and indeed you can see that calcium fluoride is just 2.5 nanometers and 2 monolayers of MOS2 on top. And even despite the small thickness of calcium fluoride, in this graph you see that the gate leakage current is very small. It's orders of magnitude smaller than the drain current, while the on-off current ratio is as high as 10^7. So these first prototypes of devices with calcium fluoride appeared better than all previous devices with sticky oxides, which do not exhibit any scaling potential and already have scaling potential and very good device performance. And most recently, we even demonstrated first field effect transistors with 2D materials, which would simultaneously have thick, less than 1 nanometer equivalent oxide thickness insulator, calcium fluoride, and small channel area of just 16 nanometers, as you see here in the CM image. And these devices also sometimes, so it's the technology is not well adjusted, but still already we can sometimes achieve near ideal subthreshold sink of 60 millivolts per decade in these devices. And this is not just one devices, but tens of devices. And this technology is fully scalable and opens further ways for fully scalable 2D technologies and for extension of the life of Moore's law. And now I would like to just look a bit broader than our research. So we achieved the first success in integration of calcium fluoride into the technologies. But actually, previously it has been shown then that such TMDs like MOC2 and MOC2 can be epitaxially grown calcium fluoride, while we use just transferred CVD grown films of MOS2, and our MOS2 films were grown on sapphire substrates. And this means basically that calcium fluoride can be fully matched with 2D technological process flow, and in future we can grow 2D channels directly on top of calcium fluoride, and probably calcium fluoride on top of 2D channels to go to top-gated devices, which will be required for circuit integration. And I started my talk with mentioning graphene, and graphene is just one material out of a huge family of 2D materials. And as you can see in this table, calcium fluoride is just also one material from a huge family of fluoride materials. So among other fluorides, which have similar structure and properties, there are some diamagnetic, ferroelectric, standard insulator, and antiferromagnetic materials. And same as graphene, calcium fluoride is just the first material, and I hope that this research will continue and many fascinating devices will be fabricated with calcium fluoride, other fluorides, not only field effect transistors, but can be also optoelectronics devices such as sensors, memory elements, perhaps supercapacitors and other devices. And this brings me to the end of my talk, and I would like to thank our sponsor, which is indeed a BRICS STI program. So this is a big project on electronic synapses based on 2D materials for neuromorphic computing. Even so, we are working on transistors. Insulators can be highly demanded for synapses, and that's why we are still the part of this big international consortium in EOF Institute. And our Russian part is led by Institute of Semiconductor Physics in Novosibirsk. And we also have a partner from Brazil, University Rio Grande, India, Institute of Science, Bangalore, and Suzhou University, China. Unfortunately, we didn't find someone from South Africa, but still it's a quite representative consortium. And thank you for your attention. Here you can find my contact and email. Thank you.
Dr. Illarionov, thank you very much for your presentation. I greatly appreciate your work, and presentation is very interesting. We have time for questions, and if anyone has questions, please forward them to the chat. We have a few minutes to ask Dr. Illarionov. Please, dear colleagues. Otherwise, you can ask by email, Dr. Illarionov. All right, let's wait a bit if any questions arise. The first question, adhesion level of calcium fluoride.
Adhesion level?
Yes.
So we didn't actually study this.
It was not studied.
It was not studied, yes. So it's quite stable material.
Quite
don't
stable
see
material.
what you actually mean. It's a quite stable material, but adhesion layer we didn't study, unfortunately.
All right. And moisture stability, what about the moisture stability? The second
Yeah,
question.
this we can answer, yes. Because actually, these devices, so the MB growth has been performed in Russia, in Earth Institute. Then this was shipped to Austria, and we performed device fabrication in Austria. So that's why it is very stable material. And even after this long transportation, the devices exhibit very good characteristics. So it's very stable in moisture and in the ambient air. So it's very stable material.
All right, thank you. Thank you very much. Let's
Thank you.
proceed to the next speakers. Today we have two speakers from India. Because of the time frame, the time for a presentation is about 6 minutes, but special thanks to previous speakers who saved some time. So the next speaker is Dr. Sayatajit Sahu. Sorry, I bring my apology if I pronounce it wrong way. So you have about 10 minutes probably for your presentation. Thanks to previous speakers.
Okay, great. Can you hear me?
Yes, yes, the sound is okay. Start, please.
Is it coming?
Yeah, you can start.
Okay, hello everyone. I hope everybody is doing fine in this difficult time. I'm Satyajit Sahu, working as an assistant professor in Indian Institute of Technology, Jodhpur. I'm thankful to BRICS for giving me this opportunity to present our research work. So today, basically, I will be giving you a brief overview of the research work we are currently associated with. And our work is related to materials for future electronic devices and their characterization. So the work is mainly divided into two parts. The first part is to find out the materials useful in electronic devices that can replace the existing materials and then fabricate devices from those materials. In this regard, the materials we are mainly working with are organic materials and 2D materials, and also some exotic materials such as topological insulators. The second part is related to energy harvesting devices, such as thermoelectric devices and photovoltaic devices, which are also fabricated using organic molecules and 2D materials. Now, so first we studied a single molecule called as DDQ, and this molecule was studied and its behavior was studied by using UHPSTM. And once we understood the molecule, we used a group of molecules to come up with a device application. We studied the group of molecules by varying the scanning voltage. Here you can see the scanning voltage is varied. You follow the blue arrow. And we saw that the molecules change their position and conformation on the surface. Now we studied the molecule in various orientation and found that different parts of the molecule respond differently to the applied bias. Here you can see this is the molecule on the left hand side of the molecule, the functional group, they give a different types of IV characteristic. On the right hand side, the upper part gives a different types of, the level of conduction is different for the upper CN group and level of conduction is different for the lower CN group. So a close observation of the surface tells us that a group of four molecules are in action when the bias is varying. So here you can see these four molecules, they are basically they play with each other when you are applying bias, and they give us some response in a very coordinated fashion. Now we found that these four molecules are basically forming an electronic counter. Now, how this counter is operated and how you get this, all these details can be found in this paper. I'm not going to go into the detail of this work, but you can find the details from this particular paper. Now, as I said that we study the molecule in group as well as in isolation. So the molecule, when it was studied in isolation, we studied it both experimentally as well as theoretically. So this curve, this IV curve that you are seeing is the experimental curve that we observed from DDQ molecule. But we try to see what is happening when we set up this molecule in a theoretical environment. So for that, we use the density functional theory with Green's function and try to find out the behavior of this molecule in the setup. And we found that both experimentally and theoretically, this molecule is having multiple negative differential resistance peak on both positive and the negative side. Here you can see this blue curve is the theoretical curve, and this orange curve is the experimental curve, and both match very nicely. And when we studied the transmission through the molecule, we found that the energy levels which are below the highest occupied molecular orbital, they are the one who are contributing towards the transmission or the transport of the charge field. Now, when we studied the transmission of the molecule very closely, we found that this behavior of multiple NDR in the positive and negative side is because of two reasons. The one reason is that the molecule is basically reducing when you are applying bias at some specific voltages only it is reducing. And there is another factor that is also responsible for this behavior, and that is the contact resistance between the molecule and the gold contacts. So sometimes at some voltages, the charge carriers are not at all interested to pass through the molecule. And that is happening only at some specific voltage. So basically, we try to explain this multiple NDR effect in the molecule by using these two reasons, that is the contact resistance and the reduction of the molecule. Now next, once we studied the molecule closely, we tried to study the molecule by preparing bulk devices, this type of devices. So to prepare the bulk devices, we glue the film of this material in combination with another polymer called as PVP. So it basically provides you a polymer matrix, right? And when we studied the IV characteristic of this device, we found that there is this switching behavior from these devices. And we saw that when we are varying the concentration of the molecule to that matrix, polymer matrix PVP, the switching direction is changing. Initially, it was showing the switching in the negative direction, but as you keep on going to increase the concentration of DDQ in the polymer matrix, the switching is shifting to the positive side. And here also we explain this behavior on the basis of two things. One, that is the molecule is reducing when we are applying bias. And the second is there is a filament, metal filament formation through the device, which is causing this kind of IV characteristic. And we also studied the other properties that can define whether the device can be used as a switching device or not. And we successfully studied this behavior from this device. Now, in many presenters, including my previous presenter, Yuri, have presented the important properties of TMDCs, which are much better than graphene. And unlike graphene, we can tune the band gap of the materials. Hence, we also use one such TMDC called as WS2, which has a direct band gap for the monolayer and becomes indirect when you use multiple layer of WS2. Now, we studied the thermoelectric behavior of WS2 theoretically by using DFT, and we found that the thermoelectric behavior of the material changes when we are applying stress or strain to the WS2. And when we studied the effect of strain on the WS2 at different temperatures, we found that the thermoelectric parameters are responding differently with the increase or decrease in temperature. And with decrease in temperature, we found that the thermoelectric parameters are showing better results. And we try to explain this behavior by using the Valley degeneracy of conduction and valence band when we were applying compressive strain and tensile strain to our material. Now, one of the interesting materials that is under tremendous research is the topological insulators. So they have derived their names from a field of mathematics called topology. In topology, they say that the material properties do not change when the material is deformed as long as the number of holes in the materials remains same. using the same concept, if we assume that the number of holes is same as the band gap, then using this analogy, we can say
1 minute.
that the semiconductors, yes?
1 minute left, 1 minute left.
Yeah, I'm almost there. The semiconductor can behave as an insulator, but in terms of electrical behavior, the topological insulators are conductors on the surface and insulator in the bulk. So this property will help studying various devices which were otherwise affected with various problems such as dissipation of heat. So we try to use one such topological material called bismuth selenide, and we try to peel layers of this material by using a sonication method and then drop casting the solution, and we found that these are materials which are isolated from the bulk, and we are now studying these materials in STM for their transport behavior. And finally, I'm thankful my students who are the workforce behind this research, and I'm also thankful to all of you for your attention.
Dr.
And I
Sak.
would like to invite all of you to the institute, which is located in the yeah. So
Oh,
thank you all.
thank you.
So
Thank
this
you for
place
the
is a
invitation.
very wonderful place, having
Possibly everyone will be interested to
yeah.
visit.
Thank you.
Once we can travel again, it would be fine. Thank you very much. Unfortunately, no time for questions. And please, everyone, if you have questions to Dr. Sahu, please ask him in private chat. And I have to give the word to the next speaker from India, Dr. Sandeep Balaji. Dr. Sandeep Balaji, you also have about 8 minutes for your presentation. 8-9 minutes. You can
Okay,
start now,
thank you.
please.
I hope I'm audible.
Yeah, I
Hello.
can hear you. Start, please.
Okay. Hello, everyone. My name is Sandeep Somavanshi, and currently I'm pursuing PhD in physics as a DST Inspired Fellow at Dr. Babasaheb Ambedkar Marathwada University, India. I hope you all enjoyed my science stand-up battle video. So in that line today, I will discuss about the magnetic fluid hypothermia in detail. So as we all know, the global cancer burden is significant and increasing day by day. So according to the World Health Organization, it is estimated to have risen to 18.1 million new cases and 9.6 million deaths in 2018. And the prediction suggests that by 2040, there will be more than 29.4 million new cases each year. So it is really a huge threat to the human beings. So cancer productivity losses due to cancer diseases are one of the major concerns of the BRIC countries, and it highlights the need for advanced diagnostics and treatment modalities through the development of multifunctional nanomaterials that allow for the point of care engineering. So currently there are various methods to treat the cancers. So some of them are conventional and some of them are recently emerged. So surgical therapy is one of the conventional methods in which tumor can be removed by surgery, but this method is ineffective in the case of deep tumors. So another conventional method include radiotherapy and chemotherapy. So they are effective to some extent, but again they have some side effects such as hair loss, eye irritation, skin problems, etc. So recently some promising methods were emerged to replace the conventional methods and provide effective cancer treatment with no or less side effects. So it includes magnetic fluid hypothermia, in which magnetic nanoparticles are introduced into the tumor and then they provide the thermotherapy in the presence of external alternating magnetic field. So the another methods are photothermal therapy and biological methods, which also emerge as one of the promising methods. So I'm focusing on magnetic fluid hypothermia. So before knowing magnetic hypothermia, let us talk about hypothermia. Hypothermia is an elevated body temperature due to failed thermoregulation. It occurs when the body produces or absorbs more heat than it can dissipate. So hypothermia can be created artificially by drugs or medical devices. So it can be used to treat the cancers and in other conditions, most commonly in conjugation with the radiotherapy. So it is known fact that cancer cells show more weakness to high temperatures as compared to the normal cells. So hypothermia system that is able to heat tumor cells in the range of 41 to 45 degrees Celsius without damaging normal tissues is desired. So the conventional hypothermia methods have some disadvantages, like it requires complex setup and targeted therapy is not possible through these methods. So to tackle this issue, magnetic hypothermia is emerged as one of the promising methods. So magnetic heat induction of magnetic nanoparticles provides various advantages over conventional hypothermia treatment. So there are a number of therapeutic benefits of producing localized heating. For example, have the sizes ranging from the few tens of nanometers and hence are easily absorbed by the tumor cells and can effectively cross the blood-brain barrier. Also opening up a new modality of treatment for cancer, for brain tumors, and can be easily manipulated in a colloidal form with numerous drug delivery methods. So you may raise the question that how these magnetic nanoparticles generate the heat. So as we all know that magnetic materials have the magnetic moment, and these magnetic moments on nanoparticles will align with the external magnetic field. So as the external field changes the direction, so the magnetic moments will be also change the directions. So this produces dissipation leading to the heating. So there are mainly three losses which causes the heat, that is hysteresis loss, Neal relaxation, and Brownian relaxation. So hysteresis losses may be determined in a well-known manner by the integrating the area of hysteresis loops, that is a measure of energy dissipated per cycle of magnetization reversal. Thus, the total heating is proportional to the frequency of the applied field and the area of the magnetic hysteresis loop. So in Neal relaxation, the nanoparticle remains fixed in a place, but the magnetic moment reverses direction to align with the external magnetic field. So whereas the Brownian relaxation mechanism is characterized by the rotational Brownian motion of the nanoparticle itself. So in the case of multi-domain magnetic nanoparticles, the hysteresis losses are dominant, whereas in single domain nanoparticles, Neal relaxation and Brownian relaxations are dominant. So this is the experimental setup of magnetic hypothermia, where you can see the induction coil along with the sample holder. So the magnetic hypothermia requires large magnetic fields alternating at high frequencies to be effective. So in practice, it is challenging to meet these two requirements simultaneously. So the circuit diagram shows one approach to designing apparatus suitable for hypothermia. This particular system provides a field of just over 0.01 Tesla at a frequency of almost 400 kilohertz with a current of 30 ampere flowing in a wire. So the high currents required for producing high magnetic fields led to a substantial residue losses in the coil and therefore significant radiative heating. So what we actually measures? So we simply measure the temperature of the nanoparticle containing fluids with respect to the time. So hypothermia heating is normally scaled to the heat capacity and expressed as specific absorption rate, that is SAR, in the units of watt per kg. A higher concentration of magnetic nanoparticles will lead to a greater amount of heating during the magnetic hypothermia as shown in this graph. So however, increasing the concentration of nanoparticle may lead to the increased toxicity and other undesirable side effects. So understanding the heat flow from the magnetic nanoparticles into the surrounding tissues and then through the surrounding tissue will be important when designing specific applications. So to apply these magnetic nanoparticles in bio applications, there are some prime requirements. So importantly, they should non-toxic in nature. So secondly, they should be stable in fluidic medium and also biocompatible and reversible. So these mainly depends on the size, surface, and relevant properties. So the size is a so the size is the important thing for the magnetic nanoparticles. So if they are too big, then they can be detected by the immune system and can be eliminated. So if they are too small, then they can be non-responsive to the magnetic field. So the ideal size of the magnetic nanoparticles should be in between 5 to 50 nanometer. So with this size range, they can will remain in the body long enough and can be easily circulated through the bloodstream. So another property is the surface. The surface plays important role in the applying these nanoparticles in real-time applications. So the surface of nanoparticles should be made biocompatible and hydrophilic by coating it with a inorganic material like silica or by some polymer groups. Also, it can be coated with a biological entity to make the particles function in a specific manner. So here you can see that by doing the specific surface modifications, magnetic nanoparticles can be used to detect virus by recognizing specific proteins on the surface of the virus. Also, the surface modifications can be done to attach the specific drug to recognize and destroy the tumor cells. So in the case of properties, the magnetic material should constantly and rapidly flip the magnetic states. That is, the retentivity of the nanoparticle should be zero. Also, the saturation magnetization should be strong enough to easily manipulate by an external magnetic field. And lastly, they should respond to the varying magnetic field to produce the enough heat. So we have prepared the series of different spinel ferrite nanoparticles by simple and cost-effective soldier combustion method and functionalize its surface by oleic acid coating. So you can see that XRD patterns of both the samples ensured the nanocrystalline cubic spinel lattice structure with FD3M space group. FTI spectra revealed the presence of vibrational frequency modes of spinel ferrites and successful coating of the oleic acid over zinc ferrite. The nano-sized spherical grains with some agglomeration of oleic acid coating over zinc ferrite nanoparticles can be visualized in FECM images. So the hydrophobic and hydrophilic surface transformation of zinc ferrite nanoparticles was confirmed by the measuring water contact angle measurements, as you can see the inset of the FECM images. Also, the DLS studies showed the prepared nanoparticles have good stability over 10 days. So image plots confirm the super paramagnetic nature of both the samples. So the magnetic hypothermia studies were carried out for the different concentration, that is for 2, 4, 6, 8, and 10 mg per ml of both the samples. So the result shows that oleic acid coated zinc ferrite nanoparticles with dose rate of 8 mg per ml are suitable for magnetic hypothermia therapies for cancer treatment. The biocompatible nature of both the sample was studied by the cell viability studies. So it shows a good biocompatibility as compared to the other magnetic materials. So similar to the zinc ferrite, we have prepared magnesium ferrite nanoparticles and functionalized its surface by oleic acid. So as compared to zinc ferrite, magnesium ferrite showed enhancement in the heating performance and requires less nanoparticle dosages. So in addition to this, we also studied the effect of carrier fluid on the heating performance. So we have studied cobalt ferrite nanoparticles dispersed in water and ethylene glycol and in combination of both. So we got some interesting results in the case of combinational carrier fluid. So recently also we have prepared the multifunctional zinc ferrite nanoparticles for bioseparation process. In this study, the zinc ferrite core was coated by silica and polymer carboxyl group to make it multifunctional. And these multifunctional nanoparticles showed better results for the efficient and timely bioseparation. So currently a variety of research is being performed on magnetic hypothermia therapy, and there is still a great deal of work to be done on understanding how these magnetic nanoparticles interact with the human body. Also, the integration of magnetic hypothermia with other therapies may provide new direction for the efficient cancer treatment. So I'm looking forward to have further networking and collaborations with BRICS researchers to tackle this issue. So lastly, I'm thankful to organizers of this forum for giving me a chance to present my work. I'm also thankful for DST and NIS for nominating me to this forum. And lastly, I'm thankful to my supervisor for motivating me to apply for this forum. Thank you for your kind attention.
Dr. Balaji, thank you very much for your work. It is also very, very interesting. If anyone has just one question, if any question. All right, if no questions in the chat, there is one question. Is there any specific material to cover nanoparticles of different types? One question.
Yeah, it depends on the what type of material do you choose. So if you choose the ferrite nanoparticles, we primarily coat it with the silica nanoparticles and then attach with it different polymer groups. So it depends on the what type of material you want to coating.
All right, Dr. Balaji. Thank you for your presentation. And there are more questions, but unfortunately, no time.
Okay.
No time. And
Okay,
you can answer those questions in the chat to other
sure.
speakers. And we have to proceed to the next speaker. The next speaker is Dr. Jianku Zhao. Jianku Gao. I apologize if I pronounce it wrong way. Dr. Gao, your presentation might have low resolution. Just try to launch it. If it is not that visible, we will just try to describe your work.
Okay, I will try. So what should I do now? Let's wait for a moment. I should share. I didn't see how to share my screen.
So there is a button, screen demonstration.
But I didn't see it. I don't know what happened. Very sorry. I didn't see the button. Sorry.
Screen demonstration or share screen.
No, this button.
Share screen.
Oh, sorry.
You can start describing your work. You can try.
No, sorry. Now I can see it now.
Yeah, if it is difficult to launch the work, you can start demonstration.
Hello, everyone. Can you see my screen? Can you see my presentation?
Yes, we can see it. I can see it.
Okay. Hi, everyone. My name is Junko Gao. But if I show... How about this time?
Yeah, it is fine. It's fine. Yeah, start.
Okay.
Please.
Okay. Good. I'm sorry. I met some problem here. My name is Junko Gao. I come from Zhejiang Science and Technology University, China. Today, my topic is about titanium-based metal organic frameworks for photocatalysis. There are three parts of my topic. So first, I would like to introduce some background. As we know, our society face very serious environmental problems, and photocatalysis by utilizing solar energy is one of the most promising method to resolve these problems. As you can see from this picture that uh, the visible light occupies about half of the energy of solar energy. So it is highly desirable to use to design materials with strong absorption in the visible light region for efficient use of solar energy. As we know that titanium oxide is the first and the most studied materials for photocatalysis because titanium oxide has the advantage of good stability, low toxic, and also very high activity. Also, it is can be facilely synthesized. Also, its cost is very low. But this materials also, this materials have one disadvantage. This is its weak absorption of visible light because we all know titanium oxide is white color, so it cannot absorb the visible light. So it cannot utilize the whole solar energy. So it is highly desirable to design new semiconductor materials that can utilize the visible light. As we know that metal organic frameworks is one type of new porous materials. It can now it have this materials has very promising applications in gas storage and separation, also catalysis. For MOFs, they have the advantage of strong. They have very high surface areas, and also their structure are diversity and tunable. They also have tunable pore size and shapes. As you can see that in the last few decades, the studies on MOFs is increasing very fast. We can see that is increasing very fast. Also, because of this, there are good advantages. Metal MOFs, they have also promising materials for photocatalysis, and they are widely used for such as photocatalytic water splitting, photocatalytic CO2 reduction, and also organic synthesis. We can see from these two figures that in the past 10 years, the researches on MOFs for catalysis are increasing very fast. We can see that, including the papers published in the last 10 years, and also their citations. For titanium-based MOFs, because I think they have both the advantages of titanium oxide and also the advantages of MOFs. So titanium cluster-based MOFs, they are the most promising photocatalysts in MOFs. Also, titanium-based MOFs, they have already widely applied in photocatalytic hydrogen evolution, CO2 reduction, and also dye degradation, etc. The first and the most studied titanium MOF is the MU125. It was first published in 2009 by Ferry. This is the first titanium-based carboxylate MOF. Because this MOF, it has very large BT, but this we all know that this MOF, the color is white, so it can only utilize the UV region. It cannot absorb visible light. This is its disadvantage. Also, titanium morphs, they are very hard to synthesize because the precursors can be easily hydrolyzed into titanium oxide. So it's very hard to form titanium-based morphs. In the last 10 years, titanium-based morphs are are growing fast, but there are still limited numbers of morphs in this area. I think now there are still 20 morphs. Also, these morphs, they are the nodes are from single nodes to clusters, then to the sheets. Next, I will introduce some of my works on these areas. The first one is the NTU9. This is my work studied when I was a postdoctor in Nanyang Technology University, Singapore. From this, we can see that in this morphs, the color is red, and also this is the first single crystal morph, titanium morph-based morph. We can see that this morph has a large surface area. It's about 900. Also, this morph is two-dimensional. The layers are stepped by hydrogen bonds. So we call this like a graphene. This is a graphene-like materials. This material can be widely utilized in gas separation. Also, we can see that it's very. This is a very beautiful red crystals. It corresponds in the visible light region. Hello?
Hello?
Is
Yeah,
everything okay?
Yeah, it is still okay. You have about 3-4 minutes.
Oh, 35 minutes.
3 minutes. 3 minutes.
Oh, 3 minutes. Okay, okay. Sorry, I will go fast. It can be used for photocatalytic decomposition of organic dyes. We can see that after 10 minutes, the dyes are decomposed. Then we think that morph are layers, so we just made some nanosheets. Also, this nanosheet can be very sensitive to ions. You can see that we got the nanosheets, and it can detect the ions very fast. Last is my recent works. We used the 3 organic ligands to construct titanium oxide rod-based morphs. This morph have 1D titanium oxide rod. You can see that also they have bigger, they also have large surface areas, and also they can be made in nanoscale. And also they have quite strong visible light response. These 3 morphs, they can be used as hydrogen evolution. You can see that the last one, STU3, it shows the best for the activity in all time morphs, because you can see that because it has very large surface areas, and also it has titanium oxide rod structure. Okay, last part. We make a conclusion that a series of titanium oxide, titanium-based morphs with visible light photocatalytic properties were successfully prepared by using crystal engineering principle. Also, we can modify the morphology under the visible light under the band gap. So we can improve the photocatalytic efficiency. Last, I would like to thank my collaborators, Professor Guo Dongqian and Professor Wang Linchen. Thanks very much. Okay, that's all.
Dr. Gao, thank you for your presentation, and we have time just for one question. So
Okay.
the first question, do you see antenna effect in photocatalysis?
The efficiency?
So do you see photo effect in photocatalysis?
Let me
And
check.
another question, how did you recycle your MOF?
Recycle it because there are nanostructures, so it's hard to recycle them. But
So it is hard to recycle them. And is there any leaching observed?
yes.
Leaching is also observed. All right, you can
Yes.
answer the questions in the chat to other speakers. And thank you one more time, Dr. Gao, for interesting presentation. Thank you very much. And today we have to proceed to the final speaker of our group of presentations. Is Gillian Miss Gillian Mahumani from South Africa. Hello.
Hello, how are you?
I am good, thank you. So I also hear you. You can start your presentation.
Okay, let me just share the screen quickly. Right. Okay. Right. Okay, good day to you all. My name is Gillian Mahumane, and I'm a PhD student from the University of the Witwatersrand, South Africa. I am very happy to be sharing this work here at the FIT BRICS Young Scientists Forum. So our work is focused on the material sciences aspects of the conference, particularly looking at bioarchitecture mimicking medical materials, where we were looking at fabricating a drug-loaded biomaterial scaffolding system for potential biomedical applications. So
Sorry, Miss Mahumani, your picture is bugging. Possibly you experience difficulties with the internet.
Sorry?
The internet connection, something is wrong with the picture. You might experience, you might have a low internet connection.
Oh, heavens. Can you hear me? Is everything fine now?
I can hear you, but something is wrong with your screen.
Oh, gosh.
Does anyone see the demonstration?
Okay. Can anyone see the demonstration?
Me not, me not. Oh, no one can see it. Yeah, the presentation is not visible.
Can you see now?
No, me not. No one can see it.
This is horrible.
So otherwise you can try telling your demonstration. You can just describe your work. If the presentation and screen doesn't work, you can.
Okay, so basically, So there's this disruptions to the quality of life that result statistics are being recorded. For example, there's poor trauma registries, and most figures are based on admission, and they don't include pre-hospital deaths, which account for about 50% of all traumas. For example, in South Africa, my country, the tracking of traumatic brain injury is very difficult due to poor hospital record keeping, and suboptimal funding has been made available for epidemiological monitoring and surveillance of trauma. In addition, interpersonal violence is a frequent cause of both trauma in general and traumatic brain injury. So surveillance and interventions are sorely lacking. And by this, I mean therapies and funding and dedicated research centers and human resource. So there is immense opportunity for researchers worldwide to contribute to the many problems surrounding traumatic brain injury. And what we decided to focus on is the lack of therapies. Why is there a lack of therapy, and how can we contribute to the solution? So this is very unfortunate. Oh gosh. Okay, so there are several factors. Can you all hear me still?
Yes, I can hear you.
Okay, so there are several factors contributing to the challenge. And when something penetrates the brain, for example, there's a stab wound to the brain tissue, it disrupts the connections and creates a distance between the neurons and the supporting structures. So the second challenge is the hostile environment that is created at the injury site from the formation of things like glial scars and the accumulation of inhibitory molecules and the secretion of free radicals via the breach of the blood-brain barrier. So this is a double-edged sword, because on one hand, the brain forms this glial scar in an attempt to protect the surrounding networks and healthy tissue from secondary damage. However, this is at the cost of regenerative potential, because now the cells cannot survive the hostile environment. And so even if they do, they cannot penetrate through the scar. So what we needed to focus on is creating an alternative at the lesion site to support the cells and the healing efforts of the brain. Okay, so this is where tissue engineering comes in. So the three-dimensional scaffolds have shown various degrees of experimental success, indicating their great potential for development as treatment options. However, there is yet to be a 3D scaffold of consummate effective clinical standards. So a 3D scaffold is supposed to mimic the tissue building requirement needs. And when we talk about tissue building requirement needs, we're talking about the extracellular matrix. And what I would have shown you if I wasn't having this nightmare was that the extracellular matrices of various tissues are different in structure. So the architecture is unique to the tissue properties. And the brain has been described as resembling foam, or a porous, fluid-filled, saturated solid we meant that the scaffold would mimic brain tissue architecture. So we decided to make a 3-in-1 system wherein nanofibers are embedded into a cryogel scaffold, followed by filling of the structure with a hydrogel. So the polymers that we used, we chose based on a selection criteria. For example, they're FDA approved, and we're looking at processability as well throughout the fabrication process. Will they be able to withstand that? And how close they will allow us to get to the extracellular matrix. So for example, we use hyaluronic acid, which is the structural backbone of the brain extracellular matrix. Proteins, polylysine, gelatin, elastin would not only help us modify the stiffness and the strength of the material, but also it would facilitate cell attachment. And N-acetylcysteine was incorporated for its antioxidant properties as a therapeutic cue. And PLGH has also shown a therapeutic potential. And a cross-linker was added to improve the aqueous stability of the materials, because most of these materials, like hyaluronic acid and gelatin, are water soluble, and the brain has been noted to be estimated of about like 80% water. So we wanted to make sure that it would be stable in the brain. So the scaffold was fabricated in a stepwise process. First, nanofibers were formed using an electrospinning technique. This was a very flexible technique, and the images that I was about to show, I think I'll share the presentation if anyone is interested, showed that the fabrication process is very flexible. So you get different types of fibers depending on how you play with the parameters. But the nanofibers that we obtained were similar to the fibers noted for brain tissue. They were randomly aligned, and also they were within the range of 500. I'm back. Okay.
Yeah, but
Within the
unfortunately,
range.
a few minutes left, 3 minutes left for the time. And
3?
yeah, around 3 minutes, unfortunately. Because we have coffee break after, and so something is wrong with the internet connection of Miss Jillian Mahumani. And we have, let's wait a little bit. If the internet connection of her doesn't work back, I will announce you the next activity. In 4 minutes we have coffee break. After the coffee break, we'll experience online experiment from the laboratory. And please stay here. During the experiment, you can forward the questions to me, to the chat, and these questions I will be forwarding to the laboratory staff. And you have a chance to participate in the experiment online. Please ask the questions in the chat, and I will forward them, and they will be answered. I will forward you the answers. There will be a moderator who will get feedback from the laboratory and answer your questions. It will be quite interesting. So yeah, internet connection, no one can be secured, and don't worry guys, sometimes it happens. So no one can be secured from the internet. We also experienced some internet difficulties a few days ago. So don't worry, it's fine. Probably you, Dr. Ms. Mahumani, can share her presentation with others through the personal cabinet. I think it will be very interesting to have a look at the presentation and work which is performed by Ms. Mahumani. All right, I have to announce coffee break now. Oh, you are back, Ms. Mahumani. You are back.
Yeah.
You can make a short conclusion just for 1 minute. Make a conclusion of brief conclusion of your work.
Okay, so basically our tissue-based multi-composite approach enabled us to mimic the 3D hierarchical structure through the use of nanofibers embedded in a cryogel system, followed by filling of these pores. And then our scaffold also showed potential for cell application, because the neural cell lines that we tested were viable, and then also to serve as an implant, because histology showed that the scaffold did not the tissue actually encompassed the scaffold and did not eject it in any way. And moreover, the scaffold functioned as a gauze would in a surgical setting where it actually stopped the tissue from bleeding. And we also saw drug delivery potential because we saw a biphasic release of drug as well. So that was in our way of actually contributing towards the efforts towards traumatic brain tissue engineering.
Jillian, you are also not online.
There.
Something is really wrong with the internet. All right, sorry, time has finished, and I have to announce coffee break now. Please stay here, get back in 15 minutes, and let's participate together in online experiments. And I will also see you tomorrow. Thank you for all the presentations and reports, and a very productive day 4. Let's watch online experiments.
One kiss is all it takes. Falling in love with me. Possibilities. I look like all you need. Let me take the night I love real easy. And I know that you still wanna see me. On the Sunday morning music real loud. Let me love you while the moon is still out. Something in you lit up heaven in me. The feeling won't let me sleep. 'Cause I'm lost in the way you move, the way you feel. One kiss is all it takes. Falling in love with me. Possibilities. I look like all you need. One kiss is all it takes. Falling in love with me. Possibilities. I look like all you need. I just wanna feel your skin on mine. Feel your eyes do the exploring. Passion in the message when you smile. Take my time. Something in you lit up heaven in me. The feeling won't let me sleep. 'Cause I'm lost in the way you move, the way you feel. One kiss is all it takes. Falling in love with me. Possibilities. I look like all you need. One kiss is all it takes. Falling in love with me. Possibilities. I look like all you need. See wonderland in your eyes. Might need your company tonight. Something in you lit up heaven in me. The feeling won't let me sleep. 'Cause I'm lost in the way you move, the way you feel. One kiss is all it takes. Falling in love with me. Possibilities. I look like all you need. One kiss is all it takes. Falling in love with me. Possibilities. I look like all you need.
I understood loneliness before I knew what it was. Saw the pills on your table for your unrequited love. I would be nothing without you holding me up. Now I'm strong enough for both of us, both of us, both of us, both of us. I am a giant. Stand up on my shoulders. Tell me what you see. 'Cause I am a giant. We'll be breaking boulders underneath our feet. I am, I am, I am, I am, I am, I am a giant. Oh, I am, I am, I am, I am, shake, throw the weight in the dirt under me, yeah. I'm gonna shake, throw the weight in the dirt under me, yeah. I'm gonna shake, throw the weight in the dirt, yeah. I'm gonna shake, throw the weight in the dirt, yeah. I'm gonna shake, throw the weight in the dirt, yeah. I'm gonna shake, throw the weight in the dirt.
One Young Scientist Forum. Now it's time for the lab experiments. We will see 5 experiments held in 2 different labs. They will be explained by Sergei Sapozhnikov and Pavel Taranenko. In case you have any questions, you can write them in your Zoom chat rooms, and we will be able to forward at least some of them to our scientists to hear to what they have to answer. So right now, please enjoy the lab experiments.
Hello, everybody. We are in the laboratory for experimental mechanics of South Ural State University. As you know, mechanics is the oldest science, but it is around us to deliver safety and comfort. Let's go to experiment number 1, connected with car step platform vibration tests. Please, Pavel. You know, any modern car is nice, but sometimes dangerous by suddenly failing. That's the reason, before the use of cars, to test their components carefully. This is done in order to confirm the strength and reliability of the structure and make sure that the car elements do not fail after a short operation. One of these tests is vibration testing. Existing structural elements are placed on a vibration stand and simulate in a laboratory the load arising in real operating conditions. The online experiment will demonstrate vibration tests on the step platform of the modern Kia Seltos car. Now you can see experimental facility, shaker and sleep table. Test object, as I said, step platform of Kia Seltos car. The schedule of the experiment is: before the experiment begins, a step platform of Kia Seltos car will be installed on the vibration table. You see now it's done. Next, the load program is set on the computer, the level of acceleration and excitation frequency. Now, vibration table system activated. The control system is activated also, and the table of this shaker is set in motion. The operating mode is displayed on the computer. You may see them, and control system screen. After a while, the experiment stops. We make sure that the step platform remains intact. You see, it's okay. And no rupture can be put into real operation condition. I can add that this structure consists of aluminum part and plastic parts on the end. And if these parts are good, this step platform will be good in operational conditions. So the noisy atmosphere is finished, you can ask me if you have a question, please. I guess it's clear.
Yeah, no questions
Absolutely.
so far.
No question. Okay. Okay. Let's go to the experiment number 2. Okay. This is our new point of view, point of attention. This is drop tower. Drop tower. Very nice machine. It can apply dynamic loading to the sample or piece of structures just in this chamber. This chamber can be cooled or heated before the test. And now you can see all details of this machine, and engineer Anastasia will close the doors, but you see a sample, small prismatic sample with groove. This sample will be loaded in bending dynamically, and if the load will be high enough, this sample will destroyed into 2 parts, and we will see the result. Before the production of valuable products and put into operation, the properties of the material from which they are made are determined. It is needed, for example, for pipelines and transport oil and gas do not collapse when internal pressure is applied. Before the pipeline is manufactured, the steel properties are checked for compliance with the required characteristics. To do this, the number of mechanical properties are determined: ultimate strength, yield strength, plasticity, impact strength. Now we will use impact testing machine. Yeah, please. Put. You will hear drop. And after that, we'll see the result of the experiment on the screen as a function of load versus time. Just a moment. All parameters will set. Initial speed, height drop of weight, and impact energy. You will hear sign like beep. Okay, experiment is finished, and several seconds to computer take all results, and after that you can see on the screen this function as I said before. Yeah, and please open the door, Anastasia. Just a moment. The machine will be prepared for next experiment and safe to open the door. It's okay. We can see the 2 parts of one sample, and one part is lost. Yeah? Where is it? Jumping up. Okay. Okay. Put here, please. You see the groove, and from this part the crack was going through the thickness of the sample, and the test is finished. You can see different objects for testing on this machine. This is the same test for fracture toughness, and here a small sample for the dynamic tension. And this is impact test of composite materials with round support and then drop inside and cracks on the back side. After that we cut sample and test it for residual strength. In this sample you can see plastic with the trace of impact and the kind of hill on the back side you see. This is the result of dynamic loading different materials, metals, alloys, superalloys, composite materials, and plastic. That's all. The second experiment. If you have questions about drop tower and dynamic testing, please, I'm ready.
Yes, there are several questions. One of them is about the first experiment. The question is, did I understand correctly from the first experiment that Kia Seltos's part is quite reliable?
Now we can say yes, because Kia Seltos step platform is absolutely without defect after vibration test, and we can say that exploitation of this part will save.
All right. The next question is, can we use this device for the soft materials?
Which device?
I don't know. That's what they wrote in the question. I think the one where you tested the sample.
If the question was about shaker, yes, why not? But soft material will have much more amplitude of vibration. It may be some problem for determining this displacement. If the question was about drop tower, yes, we can use it too, but energy of impact will be not so high as for metal sample.
Several more questions. Is the rate of vibration altered? And what is the maximum and minimum points in meters per square second? Question from India, from Sayantan Sinha.
In this shaker, we can apply acceleration up to, if I remember, 1000, 100 G, no more.
All right. Another question is from Prasenjit Ghosh. What is the sample specification, and why was the groove made?
All tests provided with standards, and the dimensions is according to standards, especially for toughness. We have this sample with size 10 millimeters to 10 millimeters and 60 millimeters long. Groove is special in the center to locate crack in needed place, and all the dimensions according to standard. I don't remember real number of this standard, but it's very well known in scientific literature.
There are a few more questions. What was the yield strength of the sample, if you remember?
For this steel, this is low carbon steel with yield stress strength about 300 megapascal.
All right, thank you. Next, what is the purpose of this test with respect to practical application in machines?
This purpose of this test connected with sometimes choosing one or another material, because in real structures we always have stress concentrators, and the possibility of sudden failure is not 100%. So we need to test different materials and choose proper materials, maybe to change some parts after 10 years or much more years after exploitation, old parts to change for new, and these new parts should require some rules, and checking of fracture toughness is obligatory
Great.
for material.
Yeah. Now a long one. A lot of data must be generated from these experiments, the first and the second. What type of predictive experiments can one derive from this to simulate car accidents as well as determine the physical properties of less known alloys and compounds and their response to stress?
As I truly understand the question, it's not short question, because for real materials, for real parts, for real structures, at first we use finite element modeling with taking into account mechanical behavior of steel or alloys, and after right calculation, we try to check our calculations with these experiments in our laboratory. If experiments compare good with calculations, then calculations is right. And then we can go to next step to prepare production site, and then to exploit this construction, this structure. If not, we should change maybe some materials or make a model, a finite element model, more correct with more details. And this cycle is not one. Sometimes we change materials or change subject several times, but finally we will get proper material, proper structure to safe use for people.
Great, thank you very much. Some more questions. How dynamic are the data sets and what features are collected from these dynamic load experiments?
How dynamic?
Yes.
Because drop tower is a dynamic machine, all period of contact impactor and sample may be 10 or 12 microseconds. So we have acquisition system with megahertz frequency.
All right. A question from Anton Nurkenov. Can you give examples of projects implemented within the framework of creating digital twins based on the test results?
We have not one, but less than 10 projects with digital twins, because all modern structures, all modern projects are not only experimental, but connected with different kind of modeling, different depth of this modeling, and digital twin is special things to better understand what we can change in real structure, not getting experiments, but only testing with this twin. We have next experiment will show flow meter, and for this subject our team created digital twin, and they can tell you more than me.
All right. We have a question from Yevgeny Alexandrov. What is the strongest material you studied?
I can say that about 2000 megapascal ultimate strength. This is bulletproof material steel. And more strength material is carbon fiber reinforced plastic along fibers with ultimate stress about 3000 megapascal.
Great. And one more question. Let's say that an experiment shows a bad result. How to determine what you have to change in the material to make it stronger?
It's not a question for me, for us, because our laboratory is a laboratory for testing materials, not for production materials.
Great. Well, I guess that's it for the questions so far. Why don't we move on to the next experiment?
Okay. Let's go to third experimental place. So this is effect of gas bubbles on flow meter reading. Please, Pavel. You see the Coriolis flow meter, which is designed to determine the mass flow rate, for example, of oil and gas products. This flow meter has a very high accuracy, which is reduced when gas bubbles enter current fluid. Moreover, there is even a shutdown to the device. Thanks to improvement of the flow meter, it's possible to ensure the stability of this operation, especially when gas bubbles appear in the flowing fluid and even when there are quite a lot of them. However, the measurement errors remains high enough. There is test rig, a flow lab with flow meter through which water is spilled with a mixture of air bubbles. Do you see these bubbles? Pavel? Add, please. Okay, many bubbles. The operator turns on the power and water pump is set and mass rate of flow going first. We observe flow meter readouts. Air is in flow. Okay. Pavel, is it possible to see the change of flow in your apparatus? Just a moment. Some changing flow. Okay, you see the changing of results. And one more. Bubbles, you see, significantly change the process. You understand, if the flow meter will not write, we will pay more. Agree? Or sometimes pay less, but it's not for us. It's okay? I think the demonstration is over, and then you may ask me or Pavel.
Yes, we are still waiting for some questions. Yes, we have a question. Can the change in flow study be carried out for both Newtonian and non-Newtonian fluids?
Oh, it's quite complex question for me, but in typical situation, liquid is close to Newtonian. It is gas or even water with gas, not so viscous. Then I cannot say something about non-Newtonian liquid in this flow meter.
Great. And it looks like we have one more question. I'm just waiting for it to appear on my screen. Why is this experiment essential? And where are the results used?
The Coriolis flow meter is the best now for measuring flow. So if we have to get less error, we need to change slightly maybe structure or design of this flow meter, or regulate some parameters of this flow meter, or maybe changing total structure of the flow, and then we will have maybe this work is not finished now, maybe to increase so-called less errors. We need to have much less errors than now. Errors of flow meter now is how many percent? 0.1% is typical error of flow meter like Coriolis. Another system for flow meter have much more error.
Great. Thank you very much. It looks like we don't have any more questions.
Okay.
Do you have any more remarks to make?
I think the specialists will give you more details, but I have only total view.
Excellent.
Maybe let's go to fourth experiment.
Yes, sure.
Okay. Let's go to this stand. Vibration-based diagnostics of rotor defect. Defects in the elements of the rotor, gears, and are determined by the sensors reading installed on the rotor supports or directly on the rotor shaft. This is. The experiment consists of a signal release from a rotor using a sensor that rotates with the shaft, transmitting the signal to a computer, processing it and interpreting it. This facility consists of rotating shaft with PCB installed on it, and there are accelerometers placed on board. Let's go to experiment. An acceleration sensor developed by our university is installed directly on the rotating shaft. Then the operator sets the shaft speed, press the button, and outputs the shaft to operating rotation. Now we demonstrate the non-defective and defective parts. Can you show, Vladimir? You may see non-defective and defective part with one teeth is out, was out. I think it's clear. It's right and bad part. Okay, thank you, Vladimir. Now we can see the result of this experiment on the computer screen. To show the results of testing with defects and without, maybe. Information is going to computer. Connected. Show, please. Yeah. It's a signal in time. Yeah. And where is defective signal? All of this. And you see here comparison of spectrum signal with ideal and real with defect shaft with supports. Blue is defected and orange is good, non-defective. So this technique allow us to know where is defect part without disassembling. This item is item of Vladimir PhD thesis, so it's very nice modern investigation. That's all. Thank you. Please question.
Great, thank you very much. I hope Vladimir succeeds in his thesis. We have a question
I think yes.
Yes, we have a question on the previous experiment.
Okay.
Do you ever measure the different viscosities of liquids or just flow rate in water?
Typically water with additives.
Okay.
At room condition. The question was about Coriolis flow meter. Maybe different temperature or viscosity, Pavel? Yes? The author of this machine say they tested different liquids with different temperatures, but not so high viscosity for that.
All right, thank you very much. We have a question from India, from Avinav Sharma. Is this an in-house calibrated setup?
Calibrated for
I think
Coriolis flow meter?
Yes, they mean, did you calibrate it yourselves, basically?
Because we were working with a real company to production of these flow meters. They have a calibration system, and after that we used this device in our laboratory. We need to understand that calibration system is quite big.
Yes, of course. Thank you. It looks like we do not have any more questions.
Okay.
So any final remarks? Do I understand it correct that it was your final fourth experiment from this laboratory, right?
Yeah, but it's not all experiments we can do this. We have much more machines, techniques for making experiments, not just in this laboratory, because laboratory for testing materials is not only one place. We have at least 3 places for static testing, this laboratory for dynamic testing. We have not so long time for show our abilities, so this is much more interesting than others.
Excellent. Actually, we have one more. I'm sorry, yes, but we have one more question. Maybe the last one for this part of the labs. How can we interpret data from the spectra that a part of the machine is defective?
For this technique, we use special software developed by our colleagues, because it's not easy to explain into words, but you should understand we did not try to use technique without checking, and this machine we showed you with right part and wrong part, and then we connected these results with calculated results, and then we can say our methodology is right or not.
All right, well, great. I think that now we are ready to move to another laboratory to see what they have prepared for us. Thank you very much. Hello.
Hello, dear colleagues. My name is Roman Morozov. I am a employee of South Ural State University, and the thesis of my scientific work is utilization of semiconductors as photocatalysts in different type of reactions. And here now I would like to show you how do we handle with organic pollutants in the wastewaters. Here we prepared solution, model solution of methylene blue dye, which is assumed as model wastewater solution. Put it in 2 glasses, and in the 1 glasses we put our material which we prepared for the remediation, this one, and this is blank solution which we would like to use for comparison of the activity. We would like to irradiate it with UV irradiation, and afterwards we will see how active it will be in the degradation of this organic dye. So we have 2 similar irradiation sets, and now we put these glasses into it. And we begin to irradiate them with a UV spectra. So now we begin to count down to 15 minutes, and after this the reaction will be ended, and the solution should be transparent and white without any traces of the methylene blue dye. So now I would like to tell you about the principles of this phenomena. This phenomena is based on the photocatalytic effect, which occur when our material, that is semiconductor, absorbs UV light, and in its structure begins the separation of charges. Electron goes to the higher energy level, and another charge is hole, which has high oxidative power. So we prepared our materials from titanium dioxide, which is known to be one of the most popular photocatalysts. This compound is very abundant in nature. It's cheap enough, non-toxic, and so we use it widely for the remediation of waters and for different other reactions. In the South Ural State University Nanotechnology Center, we developed a new way of preparation of this material. As you know, titanium dioxide has some drawbacks in its application. Its most active allotrope modification, NTAS, is not stable, first of all, and another drawback is irregular shape. Here we developed a special way of preparation which we call the peroxide road, which allow to prepare spherical shape particles with desired size, which are desired to use in flow processes, and these particles are very useful to handle with. So the essence of this preparation way is utilization titanium peroxide complex as the precursor of titanium dioxide. Firstly, we prepare colloidal particles of titanium dioxide, then we dissolve them in hydrogen peroxide with formation of transparent orange or green, independence of pH value, solution of titanium peroxide complex. Then afterwards we can prepare our particles with desired size through different ways. We can precipitate our spherical particles by exchange of the solution. This phenomena occur because this complex is not stable in organic solvents, for example methanol, propanol, and so on. Or we can treat it hydrothermally, and as we know, this complex is not stable at high temperatures, at about 200 degrees. Afterwards, we can dope these titanium dioxide particles with, for example, silicon dioxide, which is known not very active in photocatalytic reactions, but in doping it may be helpful because of high adsorption capacity for the degrading matter, and so on. These materials were treated hydrothermally, and afterwards we prepared grains of few millimeter sizes, which are more useful in, for example, flow reactions or large-scale utilization, because they may be remediated or washed without a loss of them. The layout of this material, it looks like small particles, about 2 millimeter size. So time is going, and soon the reaction will be ended. So our results of our work were also used not only for the remediation of organic matter, but also we proceeded a few chemical reactions, reactions of organic synthesis, which are easily activated by the solar light. So this material can be also doped with other semiconductors, and all solar light may be used, and the spectra which is able to activate it may be widened. So now the time is going to its end, and now we can switch this one off, and so firstly we can see this material, which one is has no photocatalyst, and we can see that this material retains its color, blue color of methylene blue dye. So another glass contains the solution with our photocatalyst. As we can see, during this short time, methylene blue dye was completely degraded to water and carbon dioxide. This is a very effective process which gives us the opportunity to degrade not only methylene blue dye, but also very hazardous matter such as phenols and so on. So this is it. I would like to listen to your questions, dear colleagues.
Yes, we have several questions. Thank you very much. So the first one, first compliments on the great work. And what oxidant do you add to produce the hydroxyl radicals with titanium?
We did not use any special oxidant. We just used only UV irradiation, and through this process in the structure of our photocatalytic material, oxidant appears by itself. In our case, holes serves as oxidants.
Okay, thank you. A question from India, from Sonalika Agarwal. Is there any effect of different morphology of nanostructures on that?
Yes, sure. We developed the spherical particles of photocatalyst. As you know that this shape is very helpful for the flow processes, and nevertheless that we also developed the procedure how we can control the size of these particles by changing different organic solvents.
Thank you. The next one. Has your group already performed tests in a pilot reactor or similar?
In a pilot reactor, not yet, but we are going to prepare it. I think it will be done in the next year.
Thank you very much. The next one. What is the band gap of your semiconductor? And what type of semiconductor are you using? NPN or PNP?
We use titanium dioxide. Band gap is equals to 3.2 electron volts. And as it is titanium dioxide, it has a negative type of conductivity.
Thank you. Have you studied the oxygen defects in your material?
Oxygen defects, yes, we studied, we performed the XPS study of our materials, and we did not found a great amount of titanium in 3-valence state, and I think oxygen vacancies are not very abundant in it.
The next question is your semiconductor nano-sized?
Yes. First, the initial parts of our semiconductor has sizes which we can control from 100 nanometers up to 700 nanometers. And afterwards, we treat them to include into silicon matrix to prepare larger size grains to which will be more useful in flow process and in large scale processes.
Thank you. Several more. Have you checked the reusability?
Yes, we did it. We checked the reusability of our semiconductors for their photocatalytic reactions in 5 cycles. And we found that it drops negligibly from 100% to 98% for in the reaction of methylene blue dye degradation. And we also used them for the adsorbents, and it performs well also.
Great, thank you. We have a question from Morena. Did you add any oxidizing or reducing agent again? And are you able to recycle your material?
In this reaction, we did not add any special oxidants or reducants. And yes, we checked 5 cycles of regeneration, recycled it, and it works well.
Great. A question from India, from Priya Yadav. Do you use any specific wavelength of UV light, or maybe any specific type of
yes.
UV? Yeah.
As it is titanium dioxide, it can be activated by UV light with a wavelength less than 400 nanometers.
All right. And any specific type of UV? UVA, UVB, UVC?
We can use mild UV spectra, UVA, beginning from 400 nanometers and less.
All right. And one more question. Do you characterize the possible byproducts of this reaction?
Yes, sure. For this reaction, it mainly degrades methylene blue dye to carbon dioxide and water because we checked it in the chromatograph, and this is it.
Thank you very much. It looks like we've run out of questions by now. Do you have any more remarks to make?
I would like to thank for attention all of the colleagues, and I would like to, if they want to cooperate with us, they can do it easily.
All right, thank you very much, Roman. Oh, actually, we have more questions. I'm sorry, if you are still here, we just received
yes.
several more. Where are you currently collecting and storing the data for the various experiments that you perform? And do you have a specific instrument to collect and measure these data in real time?
For this device, we measure the UV absorption spectra on the spectrophotometer, and we have also a chromatograph, and all of these devices has very detailed made programs which allow to make with the data everything that we want to do.
All right. One more question from India, from Swati Singh. What was the titanium dioxide dose that you used during the experiment?
Yes, we used 100 milligrams of titanium dioxide per 25 milliliters of methylene blue solution.
And following that, is there any absorption on titanium dioxide?
Yes, this is a very good question. We checked the absorption experiment, but we did not find that it's active in this stage, because if you can see this material in the solution, you can find it it has white color, but if absorption phenomena occur, the color of the adsorbent would be blue.
All right, thank you very much. Yes, there are several remarks saying that it's a nice experiment. Yes, nice experiment, and want to use it. Thank you very much.
Thank you.
Great. Well, it was very interesting, and I think everybody enjoyed the experiments just as much as we all did. And it looks like we have completed our program for today. And thank you very much. Tomorrow we will meet at regular time, as always, and we will have the results of the forum summarized. We will listen to the results of the contests. We will have some closing remarks from the heads of delegation. That's the plan for tomorrow. Thank you very much.